In today's lesson, we are going to look at analysis of data. So in this lesson, we are essentially just continuing our process of data management. So we've looked at ways to collect data, we've looked at ways to represent data. Now we're kind of looking at when we're analyzing data. So just to start off, again, looking at correlation versus causation. So we talked a little bit about this when we talked about organizing data or collecting and organizing data. And our line of best fit. So correlation is how strongly variables are related to each other, or we can refer to it as the R value. And that's usually a range from -1 to 1. And we talked about this when we looked at a line of best fit or a linear regression. When you do that, you would get an R value, and that would tell us how strong, weak, or moderate our line of best fit was to our data. Causation was the ability is the ability of one variable to influence or cause a change in the other. So we might have some variables or attributes or whatever the case may be where there's a correlation between them. But does correlation actually mean causation? Or does it actually equal the causation? So if two things are correlated, does it actually mean that one causes the other? We can look at a couple of examples. Right, so here we have a cat on a broken awning or metal awning. You could say they're correlated. The cat's in the middle, the awning's broken. But does that mean that the cat actually caused the awning to break? So even though there's a correlation, location, they're both in the middle, whatever the case may be, does that mean that one caused the other? In a more graphical sense, looking at the chocolate consumption of kilograms per year per capita, as well as the number of Nobel laureates per 10 million population, so basically the number of Nobel Award winners, we can see that there is a correlation. The more chocolate consumption in the country, the more Nobel laureates there are. It has a high R value, right? We can see that here. So does that mean that all we need to do to have more intelligent or higher, more scientific discoveries in our countries is just to consume more chocolate as a whole? Well, maybe not, right? Maybe there's not so much a correlation between that, or there's not so much a cause and effect or causation. There is a correlation because we see that here, but maybe there's not a cause and effect or a causation. Back during COVID, the blue line is daily COVID cases in the USA. The red line are reviews or bad reviews of Yankee candles on Amazon saying they don't have a scent, or basically they're saying they can't smell anything. So we see there's a correlation between these. As one goes up, the other goes up. As one goes down, the other goes down. Would we say that leaving a bad review on Amazon causes COVID? Probably not, right? There's a correlation for sure. As one goes up, the other goes up, and as one goes down, the other goes down. But would we say that one causes the other? It might be a side effect, right? We know one of the side effects or one of the effects of COVID was losing like your sense of smell or your taste. So maybe it's a side effect of that. Right, but I wouldn't say that leaving a bad review on Amazon would cause COVID cases, or having a COVID case would cause you to leave a bad review. Right, so there may be some correlation between two variables, but that doesn't necessarily mean that one causes the other. So you want to be careful of that. So there are two YouTube videos that we'll watch in class. You can look them up on YouTube. Correlation is not causation, by Sumu or Somo Publishing. So just like a kind of interesting videos, just again going over this idea that just because variables are correlated does not necessarily mean that one causes the other. So a cause and effect relationship. A cause and effect relationship is a relation where a change in the independent variable has a predictable effect on the dependent variable. And the little comic here, cause and effect relation, again, we talked about it. One event, the cause, makes another event happen, the effect. So for example, whenever a screen door appears, a cat's claws will get stuck in it. Cause and effect. Some things to watch out for when we're looking at correlations, or we're trying to analyze data as well. Aside from the cause and effect and causation, we want to look to make sure, do we have too little data? Do we have a linear regression for nonlinear data? Are we using a linear regression when the correlation is weak? Are we reversing the cause and effect relationship? Are we mixing them up? Are we extrapolating or making predictions outside the range of our data set? And are we not considering the effects of outliers or influential points? Right, so these are all things to look at when we are comparing or when we are analyzing data. So we want to be careful with that. So let's go through a couple of examples. So the sales manager for an electronics manufacturer analyzed the sales of high-definition TVs relative to the company's television advertising budgets in 12 markets across Canada. The scatter plot and line of best fit illustrate the results, and we have the linear regression or line of best fit equation and the R value. So describe the strength of the relationship. What's the strength of the relationship? Well, based on what we looked at in the previous lesson, this R value is quite high. It's close to 1. So I would say that it's strong. And you might say it's almost perfect. Right? It's almost perfect. It's very close to 1. Key thing is, though, is that it's strong. Is this an example of a cause and effect relationship? Right? Could we sit here and say that yes, one causes the other? Right? Again, there may be a lot of other factors behind it, but could we say that would this be reasonable to say that it's a cause and effect relationship? So would it be safe to say that as our advertising budget increases, so does our sale of HD TVs? In this case, I would say yes. Yes, it is reasonable to believe that one causes the other. We can see that here. As advertising increases, so do sales. Maybe other things in play, but generally speaking right now we can say that yes, as one increases, so does the other. What other factors might affect television sales? Right? So what other factors might affect the sale of televisions? Is it always just the advertising, or are there other factors in play? Right? So other factors might be, where are they advertising? It could also be the price of the TV. Could be the quality, the salespeople, right? If you have good salespeople or they're in stores with good salespeople, you might be able to sell more. Could look at like how much money are people making. Is it a place that makes commission, right? That could be a factor in how well you're doing in terms of selling your TVs. So there are other factors in there that could be affecting these sales, not just the advertising budget. Isn't it reasonable to extrapolate to estimate the television sales if the market has a budget of $200,000? Right. So would it be reasonable to make a prediction if we were looking at, say, 20 all the way down the line, where we see a line kind of max out at 8? Would it be reasonable to predict for 20 or $200,000? In this case, I would say no. It's not reasonable, because that advertising budget is roughly $130,000 greater than the last data point we have. So because we're trying to make a prediction that's so far removed from the data that we have, it's hard to predict if that trend is going to continue. So it's hard to know if the trend will continue. Right? In a similar example, it might be saying if you record your height for ages 5 to 15. So you look at your height and you record it over those ages for 10 years. Would it be reasonable to make a line of best fit for that data and then make a prediction for how tall you'll be when you're 30? I would argue no, because from 5 to 15, you're growing, right? You're in an age where you're hitting growth spurts, right? You're going from a child to becoming a teenager, so you should be growing at a certain rate. Now, is that rate going to continue always? Are you just going to keep on growing forever? No. At some point, your growth is going to slow. You are going to kind of hit your highest height. Maybe you might even start shrinking, right? So it's hard to predict that far removed from our data that the trends are going to continue. If it was, say, instead of $200,000 here, maybe if it was, I don't know, 100,000, right? Because we're looking at these values 20, 40, 60, 80. Maybe if we're looking at 100,000, right? Or maybe if we're looking at maybe 120,000, right? Maybe that might be a little bit more reasonable because it's very close to our data. But 130,000 more or 13 spots to the right on our x-axis, that's a very large or far distance away to accurately make those predictions. So that's one thing we want to be careful of. Next, we're going to look at influential points. So an influential point, we did talk about being aware of that when we're analyzing our data, but an influential point is a data point with extreme values that greatly affects the slope of the regression line, or the slope of that line of best fit. So for example, a car dealer kept statistics for 1 month on the annual income of his customers and the price of the car each customer purchased. So we want to analyze the influence of the purchase by the customer with an income of $200,000. So the income was $200,000. This is the point we're referring to. So we can see that with their income of $200,000, they only bought an $80,000 car. So how does this point affect or influence my data or my scatter plot here? Well, because we have this point here, that's actually pulling this line of best fit. Because that point's there, it's pulling that line of best fit closer, or to making sure that it includes this value. So that's what we mean by an influential point. If we look at the rest of the data, if I get rid of that point, my line of best fit may look something like this, which means that if I have a customer that comes in that has a $20,000 or $200,000 income, I might expect them to be spending maybe close to $150,000, $200,000 on a car, right? So those influential points, if they are extreme values or they don't quite fit our data or our trend, it can affect our regression or the slope of our line. So in this case, the line changes. So this right here, this is definitely an influential point. If we were to remove that point and then create our line of best fit, that would give us a better analysis of our data, or a better line of best fit to use. But it is a valid point in there, so we do have to include it. You might be able to remove it and then say we remove this point because it's a one-time scenario, or it's a one-off, right? We don't see a lot of data following that trend. If you gather more data and then we find that, you know what, there are more and more points along here, then you might say, okay, you know what, let's leave that point there. Based on the extra data we collected, it actually does make sense. But for right now, the line of best fit would change if we remove that point, so it is an influential point. Lastly, looking at the regression analysis or the line of best fit, we want to look at some possible errors in the regression or the analysis of each situation. So we want to look at each of these and see, is there some possible errors? Well, here, this one's a kind of an easy one. We see an outlier. So that's the error here. Not that it's bad that we have an outlier, we just have to keep in mind that our line of best fit may not be accurate because of this outlier. For B looks like the line is good. It goes in between the data. However, if we look at the amount of data points in B compared to A, we can clearly see there's not a lot of data. There's only 5 points. So here what we would say is not enough data. Right? 5 points is tough to make a prediction. Usually you want to have a few more points to have a better or more accurate prediction, or you're more confident in what the prediction is. For C, so we have our line of best fit. However, looking at the actual data points, the data doesn't really seem to follow a linear pattern. It seems to follow something that's more quadratic. So if we have data that follows a different type of function or a different type of relationship, we can't always use a linear regression or a line of best fit. So in this case, it's quadratic, not linear. So you want to be careful and make sure if we see that our data appears to be something that's not linear, it may be difficult to use a line of best fit to make predictions. And then lastly, a regression equation with y equals 0.673x plus 7.221 and an r value of 0.126. So in this case, the main thing here is this r value. So because we have a low r value, we have a weak correlation. So if we have a weak correlation, yes, you could still have a line of best fit, but we would say that therefore you probably don't want to have a line of best fit because it's a weak correlation. So you don't want to say that there is a relationship because at best there is a weak one. And as we saw in the previous example, you can have a relationship that's not even linear and still create a line of best fit. So you just want to be careful. You can create a line of best fit for almost any any set of data if you're using Desmos or something like that. But that doesn't necessarily mean that it is the best one to use. So again, if you have a weak correlation, you want to be careful of using a line to represent that data or to make predictions. So again, the main thing from this lesson is just understanding some things we should be aware of when we're analyzing our data. And we want to be careful of saying that if there is a correlation or a large or a high R value, that means that one variable causes the other. So we want to be wary of saying that correlation equals causation. So we really want to analyze the values that we have.